Hello everyone. Today I'm happy to share with you a live code. I'll make no edits on this, and we are going to look at the potential suitable habitat for uh, a species called Salvadora persica in Namibia. So for that, we will need those two libraries principally, but we can also load um, tidyverse. Just probably we will be wrangling some um, occurrence records. In case you want to reproduce this and you're getting some errors, so probably it's important to show the versions of the packages I'm using. For the SDM, I'm using version 1.2660. For the geodata, at 0.62. And for tidyverse, I think it's 0.2 or 2.0. 2.00. In case you have very old SDM package, you can install it, of course, using either DevTools, the latest development version, either DevTools or remote. And then you provide the name of the repo /SDM. If you run this code, then you will get um, the latest version of SDM package. For now, I will comment it out. And after that, we will need species occurrence records. So first of all, we need the region of interest. So a region of interest, we'll get it from global administrative boundary or GADM function, which comes from geodata package, and then not really Zambia, but Namibia, because that's a beautiful country with deserts touching the ocean. I don't want to store that data anywhere in my local machine, so I set path to a temporary directory, meaning if I shut down my computer, that file will be gone. After getting, it's a small file, it's just a few kilobytes. It's already downloaded, I have it in my R. Now, if I want the species occurrence records, I will use SP occurrence again from geodata package. And the genus is Salvadora. And then the species is persica. And then I want to limit the records to the boundaries of Namibia, which is our region of interest. Geo is true, so that I only return records with some geo locations. I also remove zeros. That means if coordinates have both 0, 0. I know Namibia is way south and I don't expect a 0, 0 coordinate like longitude 0, latitude 0. I think those are sufficient for me. So let me see how many records are there. Ooh, no records found. Okay, maybe I used wrong spelling here. It should be Salvadora Pasica. Yeah, we have some 217 records. I would consider that sufficient for my uh, study. Um, hmm. So after getting the occurrence records, I will clean them a bit. If you check SP file, it's a data frame with so many columns, so many rows, some of which are important. Probably all of which are important, but for this uh, small demonstration, we'll just consider a few of them. So the ones we will consider include the coordinates, of course, the longitude and latitude, they're somewhere. We will also consider basis of observation so that we only um, uh, retain or keep those that were observed by people. And maybe those are just sufficient for us. We won't do too much cleaning. Let me first of all see how many records will remain as we clean. So we take our data frame and then we select longitude column, latitude column, basis of record. That's where we will pick the human observation and the rest. And what else? I think those are sufficient for me. We can check the number of rows. They are still 217. Then we can now drop NA, if at all any. Uh, After that, again, after dropping NA, we again check the number of rows. And there is that error, but not so important. So there were no NAs. Then we pick unique or distinct. And then again, we check the number of rows, how many are left, 200. So there were like 17 duplicates in our data set. After we've known that we now have 200 unique records, then we now filter by basis of record. So we filter where basis of record in, that is percent in percent. Human observation. Or maybe we check how that basis of record is, what we have in the basis of record. So we can tabulate the species $ basis of record. So we have basis of record as human observation and preserved specimen. So we don't even need to filter for this. That means we didn't even need that. And we also don't need that because both preserved specimen, these are specimen in herbarium. Somebody collected them from herbaria, voucher specimen with latitude, longitude coordinates, and identity of the species. And then human observations are those that somebody went to the field and made observation, normally from iNaturalist and some other people, and pushed to GBIF. So I think just picking those columns, dropping any, and ensuring that everything is unique is basically sufficient. So I can call that, sorry. What is, okay, something has just happened. My keyboard just switched, so I have to bring it back to what it's supposed to be. Okay, so this SPS is now the clean one. or we can call it SP clean, so that it's easier to separate from the original SP. Once we have our SP clean, we can convert it to a spatial spat vector object. So we can first of all look at the head of that SP clean. We just see longitude and latitude. So we can convert it to vector, SP vect. We can use vect packet function from Terra. We didn't load Terra, but when you load SDM or geodata, they require Terra. So by default, Terra was loaded in the background. So this is SP clean, and then pick the geometry attributes from longitude and from latitude. And as I see those coordinates, their CRS is likely EPSG 4326. That is long lat coordinate. And now we can even inspect this a bit using map view. Map view again. And then we put SPVect, and we should be able to see the points in Namibia. This is Namibia in this corner. Of course, some of them are falling in Botswana and maybe Zimbabwe. Maybe not in Zimbabwe, but majority are along the western coast of Namibia, basically in the desert. If you look at this S3 world imagery, which tells you a bit more clearly, you can see these are basically dry riverbeds, which are normally occasionally filled with water during heavy rainstorms ups, but this is just a desert environment. But yeah, I know this Salvadora persica as a species, it prefers these dry regions, and it's a useful plant, medicinal, edible by people and animals. Also used as a toothbrush, which probably is what many people know. In fact, in English, it's called toothbrush tree. Yeah, so what we've seen is that some records are in Botswana, but we wanted to have only the records. We wanted to have only the records for Namibia. So what we do is to crop. So SP crop. We crop SP vect using the boundaries of our region of interest. And if we do that, and we rerun our map view using the crop version, then we should now see that the ones that were in Botswana have been left out, and now we are only containing records inside Namibia. I mean, you will be wondering, why did they have to have this stretch touching this point? It's a long history, you can read about it. Why these several countries, Botswana, Zimbabwe, Zambia, and maybe Angola, almost Angola, were almost converging at this one corner. Probably that explains why some records are in this location, that people who came to this region picked some plants and maybe planted them in this region, or because I don't want to believe that they just existed there. Seems the interaction among these countries near this region led to the occurrence of those few records. If we decide, we can crop them, but for now, we will just use them as they are part of Namibia. Now let's look at the predictor variables, which we will use from WorldChem. So our predictor variables we'll use from world claim country. We don't want to download the whole world claim for the whole world, but just for Namibia. Here I'm using Namibia and not region of interest because it needs the character, not the vector. The character name of the country and not the sparse vector object of the extent. And the variable is bio. Again, into my temporary directory. That's all. Slightly big, 82 MBs, but we'll be able to, I mean, not really big if you compare with several GBs of data that we normally work with. Cool, so that is already downloaded. Might take longer in your computer depending on the speed of your internet, and might also be super fast depending again on your speed of internet. So when we look at the spreads, it has got 19 bioclimatic variables for Namibia. But just like the the occurrence records, if we plot this, we see that it's just a rectangle around Namibia. So it's basically taking the extents uh, of Namibia. So we crop again. This basically, actually, we don't even crop it. It's already cropped to the extent. We mask, like we ensure that areas outside Namibia are not available or are NS. So we mask the predictor variables using the region of interest. So if we do that, and again, we check the Pred's mask. Sorry, those are so many images. I should have just selected one band or one layer. Can sweep my plotting area and then rerun this, and we see just that it's now within Namibia. Now there is this issue of highly correlated predictor variables, which you can handle in so many ways, including PCA, running PCA. For this, we'll basically use variable inflation factor or USDM package, and to remove highly correlated variables. So from Pred's mask, we are running VIF core. This function has nice arguments like threshold. You can alternate, change that. Default is 0.9. There is also this keep, where if there are some predictor variables in Preds which you don't want to drop, regardless of their collinearity, multicollinearity, you keep them. You provide them as a vector. So if we run this, we get an output which tells us the variables that are highly correlated, and we can exclude them. Exclude function is also from USDM. I mean, you can manually, whichever way you like, you can manually subset this sparse raster object to retain only those that are not highly correlated, but exclude is an interesting way or a simple way of doing it. So you just provide the data and everything which is in V you exclude. Multicollinearity check is still running. Remember there are 19 predictor variables. They are paired and run, and the inflation factor is checked. And then finally it will end up with, dropping the highly correlated ones and keeping those that are not highly correlated, which will help the model to learn something. Mm, as that is still running, once we have this, we will go straight forward to building our species SDM data object. And SDM data object takes a formula, which is, oh, I think we did not even give a species column name. And then we tell it what our training data is. And then we'll also talk about predictors. And then we'll also talk about background or BG. We'll also give it the background data that is still running. So let me go for the background. We'll get background using background function, which also comes from SDM package. And in background function, we have X, which is the sparse raster object, which will be this. And then we have N, I think, or Y, which is the size. Okay, so this has finished running. So we can do the exclusion. Maybe if you want to check what V is, it tells you that 5 variables from the 19 input variables had multicollinear or collinearity problem, and they have been excluded. So if 5 have been excluded from 19, we are left with 14 variables. And those are the ones we are supplying to the background function. N, we want them to be the same as the number of rows in SP crop. So SP crop has got 178 points finally. So we can set this to maybe 1,000. I mean, 178 will be quite low to better contrast the background. Then which method are we using? There are 3 methods. There are 4 methods. I've captured them in my earlier videos. And for this, let me use a more complicated one like edist, because the environment here is quite contrasting. And if we use this, then we need also to supply the locations of the species, and that is given by SP-crop. Something I've realized is that our SP-crop has got no species column. So just above this, I mean, we don't need it at this stage, but I just want to add it already by using this and saying species and then assigning it to a value of 1. So those are the presence locations. So if now we look at SP crop, we'll be able to see 1, 1, 1, 1, 1. Here we didn't have it. And so this will generate for us background records, which we can supply to this PG argument. As it is still running, of course, formula now, because we now have the species column, we'll say it's species as a function of everything. And then train is SP crop. And then predictors is the predictor variables are preds used. And then the background is BG. BG basically is a data frame. If you look at BG, it's actually a data frame having XY coordinates and all the predictor variables that are in the preds used. And then we run this D. Let's pick up predictors spreads used, which is that. As it is running, we can also create the model itself and say SDM and formula is the same as in D. And then data is from the D object, which we created up here, which has all this. You can even supply this here, but it's neater this way. Then we decide on methods. I mean, this is a presence background kind of study. We have no evidence that those background are true absence. So we can use a method that respects that. Replication method, we want to use cross-validation. And then number of folds, I just want to keep it simple, 4. And I think that's sufficient for now. If it was a huge data, we will think of going to setting and adding parallel, processing it parallel. And we run that, we build the M. Once we will have the M, we will also need to make predictions. We'll use predict function, and to predict, we provide the object, which is M, and then something called new data, which will be the preds used. And I just want one layer. So I get the mean of all these outputs, like 4 outputs, I think, because every time one fold is kept for evaluating the model and 3 folds are used for training. It's running. I mean, sometimes it's good to make this parallel, to run this in parallel. But that normally depends on the size of data. If you have a lot of data, then you will consider that. It will be faster. But if you don't have a lot of data, it's not advisable because it takes your machine time to partition the work into different compute nodes or to different cores. And then after each core has successfully run, then it again takes the computer some time to assemble the output. So those two can be taking more time than even if you would have run it without parallelizing. I want to confirm that. I think it is this. If we check SDM help somewhere about parallel. Yeah, that is what the author of the package mentions down here, that only use parallel setting when you deal with a big data set or large number of models. Here we are only using Maxent. Otherwise, it make the procedure slower rather than faster if the procedure is quick without parallelizing. So that's where I picked the idea from, and I think I've tested more than enough and realized that sometimes it's not worth parallelizing. So we are making prediction of our using our model. The object here is M, and we are supplying the new data for which we don't want individual computations, but we just want the mean. So we are applying the trained model on that object. A couple of things you can check about the model include R-curve M. You can check ROC of M. You can check, you can plot the variable impotence. I think it's something like that of M. And you can also interactively look at the model output using GUI function. All these are well documented in the manual of the package. Basically, what I wanted to do was to reach here, but you can also consider going for presence absence or determination and the rest. Our prediction is still running. And I think this predict also we can use, we can parallelize it. So if you have a lot of data needing for predict to where you want to predict on, then you can make it parallel. And for example, we are using our model here has 4 IDs in it. There are 4 models here. So if we would have parallelized it, then each ID would be thrown to a separate core, and that core would run it and return the results. All the 4 cores will be busy running and returning the result once. But if we don't parallelize it, then it will run in series where one core will be used to run the first model, prediction using the first model, and then prediction using the second model, prediction using the third model, prediction using the fourth model. So it will be like about 4 times slower than if you parallelized it. But again, remember the overhead in partitioning the model into the cores and assembling the output back to a single object. So that uh, can sometimes take time. I think that's almost all we wanted to see, but it's still taking its sweet time. So why not think of other things? Mm. And then on top of it, we can also, I think I should have just added this map view as a library. It's now calling it too many times. SP cropped. Predict is really taking time. I mean, it's because each of these pixels has got 14 values, and the model is making predictions per pixel because, and it's doing it 4 times, then getting the mean. So we better be patient with the model. There are so many pixels in this beautiful country, Namibia. I mean, I also really appreciate those who walked in these dry riverbeds, maybe without a bottle of water. They were running out of water at some point. This is a clear path along the dry riverbed. They observed a tree somewhere here, which was Salvadora persica. They took the coordinates. These are super harsh conditions to be. Remember, on this side, you have the ocean, inland, you Oh, okay. There was a built up area somewhere here. Some activities going on, maybe mining. Um, yeah, who knows? Um, there is also somebody found themselves in this location. So Salvadora persica and obtained the record GPS. And these are some of the places where GPS signals are super good. So I strongly believe whatever they observed are true occurrence, basically super true occurrence records, uh, because we have uh, cloudless skies, or basically less cloudy. Um, yeah, like this region just seems there are some settlements, some people settle around here, and were even able to capture occurrence records of some species. Somebody even wandered this far. I doubt if if this region has a plant. These are some of the checks you might be interested in doing yourself when you're working with species occurrence records. My intuition tells me that this record is wrong, um, because these are just sand dunes, pure sand dunes with no dry riverbed or any possibility of uh, this species growing there. But yeah, that therefore draws my attention to this lonely point here. It might also be misplaced, or it might be correct. Mm, way up. Okay, maybe this one also could be. Normally, points that lie alone far from the rest sometimes are questionable, sometimes they are correct, because I can see some plants around here, so maybe it's just correct. Cool. So our P1 is done. We can, oh, how do I map view the M? Should be P1, and then this. Number of pixels, normally truncated. That's not a problem because we had so many pixels there, and therefore some had to be dropped. It's even struggling to show this is 50,000 or 500,000. 500,000 points. Not points, but pixels. Uh, you can increase the value by setting max pixels, but I'm not interested in that now. Yeah, so these brighter regions are the highly suitable regions for this species in Namibia. So we can do range shifts, we can project into the future, get future climate data project, we can tell conservationists, uh, yeah, because some people probably took the occurrence records there, it gets more suitable as you move further from where it was. And that's basically heading to Zimbabwe or Zambia. Those who come from that region could tell us whether this location you can brush your teeth without going to the shop to buy toothbrush. And it is toothbrush and toothpaste in one, because it has a salty kind of taste when you use it. I've used it myself, so I know how it tastes. You don't need to buy toothpaste. Cool. So yeah, I said you can also check the response curves of this model, of the predictor variables, to see how they captured the niche of these um, species. Um, Again, taking time because there's so many records. 178, not so many. And it's comparing the evaluation values that led to the metrics used. Mm, yeah, archive normally takes longer time. I don't know if this can be improved in the background to be faster somehow. Rock and get variamp normally run faster, but archive um, takes longer time. Okay, finally, we can see the response curves. This looks good. Basically, it should be unimodal. So this is a bad signal here because we don't expect a species to respond positively to something and then negatively at some concentration and then positive again, unless it interacts with something else in a very strange way. This okay, these are okay, these are okay. Basically, most of them are okay, but I'm worried about this. I mean, this is just walkthrough, so not so much of crucifixion due to few errors here and there. Our rock curve is super good, 96% on training, and test is 95.5. And which variables were important? Get variant, I think I missed some spelling. Yeah, the most important is bio6 variable, and this is based on permutation. Um, then with the graphical user interface, you can see a number of things, including evaluation metrics, those that are threshold based, and then you can use these to binarize your data, for example. Can report those that are threshold independent, grade AUC. Variable importance is the same thing we've seen with Bio6. Yeah, so let me end there. If you have any question, you can ask in the comments. I'll push this to my GitHub repo and you'll be able to reproduce it. Thank you.